In this X-Minute Math video today, we're going to be talking about how to complete the square for a quadratic polynomial. Now in particular, we're going to stick to the case where the x squared term has a coefficient of 1, just to keep things nice and simple. So to start with a simple example, let's start off with a situation where the quadratic is already a perfect square. So let's take f of x to be x plus 4 all squared. Okay, so what I'd like to do is I'd like to relate this algebraic product to the area of a square model. Okay? So just to emphasize this, let's write this square as x plus 4 multiply x plus 4. Now what we can do is we can think of this product as the area of a square whose side length is x plus 4. So let's see how we think about this. So I can think of there being part of my side lengths that have length x, and I can think of the remaining portion of the side length as being the plus 4. Now altogether, by adding, I can see that these side lengths are x plus 4, indeed. Now the nice thing that I can do here is I can chop my square up using these subdivided side lengths. So let me show you what I mean. So I can chop my square up into 4 pieces that are each squares or rectangles, and if I carry through the side lengths, you can see I get x's and I get 4's. Now using the formula for the area of a rectangle or a square, you can see this top left rectangle has area x times x, x squared. This bottom right corner has area 4 times 4, that's 16. And the other 2 rectangles, you can see they have base height 4 and x, so they have area 4 times x. So now to figure out what this product is, what this area is, all I have to do is add these 4 areas together. So what I get is my x squared plus my 4x plus my other 4x plus my 16. Now the really nice thing is, if I remember some algebra, I can see that this is exactly what I would get if I apply the FOIL method to expand out my parentheses, right? I would look at my first pairing, my outside pairing, my inside pairing, and my last pairing. If I carry out those products and add them together, it's exactly the same answer that I would get. So that's really nice. But the natural question to follow up with is, what if my quadratic expression is not already a perfect square? So what if the quadratic that we're looking at is not a perfect square? Well, we can take what we just figured out and generalize it a little bit and actually make some good progress. So let's say I'm looking at a function, g of x, and we'll write it, say, x squared plus 6x. Now what I'd really like to do is relate this back to the area of a square. That got us a lot of good progress before. So looking back at what worked out previously, well, I took the coefficient of x, right? I wrote it in the previous example, I had 4x plus 4x. I split the x term in 2. So let's see if that might work out for us this time. So let's just write this as x squared plus 3x plus 3x. Well, I haven't really done anything, but that will allow us to follow our nose just a little bit. And if we end up with another square model, let's think. Last time I ended up with x squared plus 4x. Why did that appear? Well, I had my x and my 4 as part of my side lengths. So, okay, let's see if something similar will work here. So if I take part of the side length and call it x, this time let's take the other part of the side length and call it 3. So if I do the same trick that I did before, okay, split up the square into 4 smaller pieces using these side lengths, well, I'll push through the side lengths, so I'll get x's and 3's. And now let's figure out these areas like we did before. So I got x squared as my top left. I got 3x as my top right. I got another 3x as my bottom left. And okay, I have a bottom right corner that's 3 times 3, that's 9. That's okay. But this is actually really good news because 3 of those 4 areas match up with my expression really well, right? I have x squared, I've got one 3x, and I've got the other 3x. Now, okay, there's that little extra corner of area 9 that doesn't appear in my expression, but I can deal with that algebraically just by subtracting it. Okay? So what we're seeing is I have an area made up of my 3 smaller pieces that is equal to my expression. Okay, well, one thing that I could do is I could take the entire square. Okay, so an expression for that, I can just apply my area of a square formula. So I get x plus 3 all squared. That is the area of the complete square. But I need to subtract off that little extra corner, right? I don't want that 9. So let me take that 9 and I will subtract it off my expression. So here I end up with an equivalent expression for x squared plus 6x. That is a perfect square, x plus 3 all squared, and I'm subtracting off a constant. Now, before we do one last example, I want you to notice a couple of things. What did we do here that worked really well? Okay. Well, we cut the x coefficient in half. Right, that worked both times. Okay, the 6x I rewrote as 3x plus 3x. And we also subtracted the square of that halved value. Okay, so let's think. What did we do? We had the 6x. We wrote it as 3x plus 3x. And then we subtracted 3 squared. Okay. That's how we ended up with our expression, x plus 3 all squared. Right? My 3's I put right there, and I subtracted the 3 squared, the 9. That's going to be our guiding light moving forward into our next final example. Now the last thing I'd like us to think about is, what if there's a constant term? Okay, what if the quadratic expression I'm looking at has a constant term? So as an example, let's define a function h of x to be x squared minus 12x plus 3. There's our constant term. Now the good news, just like last time, is we've already done the hard work. Okay? Because what we're going to do here is we're going to think of the x squared minus 12x separately and just deal with that like we did in the previous example. And that plus 3 is just going to hang out and we'll fold it back into the process at the end. Okay. So in this next line, I'm going to think of there being 2 separate things going on. I have my terms involving x, and I have my plus 3 that's just hanging out. Okay. So let's think about what we were supposed to do. Well, I wanted to look at the coefficient of x. Okay. Now what's worked well in the past, I've taken that negative 12, that coefficient of x, I've chopped it in half to get me, in this case, negative 6. And then if I square that, I'll get 36. And those are the numbers that I'm going to use to form my expression to complete the square. Okay. So the first thing I'm going to do is I'm going to form the perfect square using that -6. Okay, so that -6 gets used like that. I then have to subtract off that squared term, right? So that was that 36 that I've seen over there. So there's my 36, and I'm just subtracting it off right there. And again, yep, I have that +3. I definitely don't want to forget about that +3, but it hasn't really done anything for me yet. So now all I have to do is do some tidying up. So that perfect square is doing its own thing. I've then got -36 plus 3, so I'll just combine those into my single term of -33. Now we can be very confident, of course, we can have faith in ourselves and our mathematical ability, but it's never a bad idea to check. Especially when we can check. So in this instance, let's take that expression that we found, x minus 6 all squared, subtract 33, and let's expand this back out. Okay. So I'll set this up so that I can apply the FOIL method. If I now do my first pairing, my outside pairing, my inside pairing, and my last pairing, what I will get is x squared minus 6x minus 6x plus 36 minus 33. If we gather everything together, you'll see we get x squared minus 12x plus 3, which is exactly what we started with as our expression for h of x. All good. So, do you want one more minute of math? Well, you could try rewriting the expression f of x equals x squared plus 20x minus 11 using the methods that we just talked about. And if you'd like to do X minutes of math, Y more times, don't forget to subscribe to this channel.